Hello, everyone. Thank you very much. Let me come on camera here. Okay, so the here we go. I think now y'all can hear me. Can y'all hear me? You should be able. We should be good now. So I'll go ahead and get started. Eric, thank you very much for that very great introduction. And let me share my screen, and we'll go ahead and begin. So what we'll be going over today is RF interconnect design and PCB design. And we'll be looking at what happens in various frequency ranges, going from Wi-Fi frequencies all the way up to millimeter wave. And I think it's important to understand the differences in design approaches to both. And so our agenda for the meeting begins with RF design concepts. And so we'll look at some of the core concepts that support RF PCBs. We'll also look at board design principles, some materials and stack up. We'll look at interconnect design. And I'll show you some examples of RF structures, and there will be some calculations in here that kind of illustrate the thought process behind these designs. So first, let's begin with RF design concepts. So I think it's useful here to compare this to digital because with digital, especially at very high data rates that we're currently dealing with PAM4 signaling, the important concept to understand here is that the frequency in digital signals is not just a single frequency. And sometimes people, I think, who are new to PCB design and who are trying to learn about high-speed digital design will often reference the clock frequency. The reality is that in digital communications, the clock frequency is usually meaningless. What's important is the rise time, and then how the power contained in a signal is spread over different frequencies. So you can see this in this graph here. We have a lot of power that is clustered up to very high frequencies, and our Nyquist frequency is really where we care about the sampling for this digital signal. And so we're really trying to sample all of this power here, where my mouse is, in the left side of the graph. And so this time domain signal here, this pseudo-random bit signal, or bit stream, I should say, is being transformed into this power spectrum using a Fourier transform. And we also care about the loss in these lines. Now, the loss can be pretty considerable once we get out to very high frequencies. So this is for a 50 centimeter line, so that's essentially 20 inches. So this is a very long line. Now, in digital, the other piece of information that you need to know is the rise time, because the rise time is really what determines all of these characteristics of this power spectrum. So this power spectrum will be different if the rise time is different, but the power spectrum doesn't care at all about the clock frequency. Okay, so really the point here is that in digital, we're dealing with a huge range of frequencies. Now contrast this with analog or RF. We're generally dealing with a very narrow range of frequencies, and oftentimes we're only analyzing a design at one frequency. And so we care about the signal, and oftentimes if we take a time domain measurement of this signal, we'll see noise superimposed on top of it. And so you can kind of see that here in this graph, where we have what looks like a sine wave. It has a known period, t, so this is a time domain measurement. This is the time for one oscillation, and then the inverse of that time, or that period, gives us our frequency. Then if we know the frequency and we know the speed of the wave, then we know the wavelength. And the wavelength is important when you're actually looking at things on a PCB, when I mean the structure of a PCB, and that wavelength will become important, as we'll see in some examples. And then the speed is related to the speed of light in vacuum divided by the square root of the dielectric constant. So the square root of dielectric constant is actually the refractive index. So if you come from the world of optics like I do, you deal a lot with refractive index instead of dielectric constant. But in electronics, we care more about the dielectric constant. But the two are related. And so as long as you know this epsilon, which you can get from a material data sheet or from a measurement, then you know the speed and the medium. And so when we take this wave and we apply modulation to it, we now have a wave that carries some kind of useful information. And that's the entire idea behind RF communication, is we have this wave that we can generate and we change some characteristic of that wave. Now, when we send a signal down an RF link, RF links, and starting from this this die A, or starting from this package over here on the left, and going all the way through this link over to package B, there will be some loss in that channel. So typically when we look at like digital signals, we want to make sure that the digital signal is above some threshold. And as long as the signal is above some threshold, then it can be interpreted as a 1 or a 0 in the standard digital logic. But with RF, we actually have a range of possible inputs. So this signal doesn't need to be above some threshold in order to be read or received. It needs to be above some receiver sensitivity. So essentially, as long as the power is above the receiver sensitivity, so just for example, negative 30 dBm in this particular example, then we know how much loss we can tolerate on this channel. So that's another important value to know, because that's going to determine how long you can make this channel. Now, for low frequencies, maybe like sub 1 gigahertz, or maybe for something in the Wi-Fi range, the loss is not going to be a major factor that limits your design. But if you're doing something at millimeter wave, the loss really does matter, because this can place a severe limitation on what you can do in your PCB and how far you can route things. It'll also limit things like the vias that you can put onto a particular link. So each via adds additional loss in addition to the transmission line loss. So you have to consider these two together. And there could be other sources of loss that aren't accounted for in this simple model, but these waves will experience loss as the signal travels from package A all the way to package B. So the next key concept to know is, of course, dielectric constant. So I mentioned that dielectric constant. Generally, if you look at data sheets, they will give you a dk value. So digital people tend to use dk. RF engineers tend to use the dielectric constant, or epsilon. It is this epsilon r value here that will determine the speed of the wave. So this epsilon sub r is the real part of the dielectric constant. There's also an imaginary part of the dielectric constant. And then if you look in material data sheets, there's also a loss tangent, or tan of this delta. So this quantity here is actually, my apologies, is actually a ratio of these two values. The substrate conductivity also matters in the formal definition of loss tangent. However, for PCBs, we generally set this to 0, and then the loss tangent just reduces to this ratio. So you can kind of see how this fraction will simplify. So there's a really important key here, in that when an electromagnetic wave is traveling in some medium, the dielectric constant affects the wavelength. So a larger dielectric constant will cause that particular wave with a particular frequency to have a larger or smaller wavelength, depending on this value. So when we have a large dielectric constant, we have a smaller wavelength. Smaller dielectric constant, we have a larger wavelength. So if you want to have smaller RF printed circuits, you could use a larger dk value. Okay, so just as an example, many times if you look at PCB design guidelines around microwave and RF design, they will say, well, you have to use the lowest dk value possible, which is not actually true. Sometimes you want to have a larger dk because it lets you use smaller printed circuits. And larger dks, such as the dk value for this material, RT Duroid, can have much lower loss than FR4 laminates. So you can still get the lower loss, and you can get smaller circuit sizes. But eventually, the circuit gets so small that you can't manufacture it with a standard PCB manufacturing process. And so then you actually do want to use a smaller dk, because a smaller dk is going to give you a circuit that you can actually manufacture with the lower loss than the standard FR4 grade materials. So I mentioned before that when we have a signal and we apply modulation to it, that modulation is going to provide the information carried by this signal. And so when you look at an unmodulated signal in the frequency domain, and this is generally how we analyze RF signals, there's just one peak here in the frequency domain. And it essentially says that all of the power being transmitted in your signal exists at one specific frequency. In reality, when you have a modulated signal, and that's exactly how you have to transfer information over wireless links or over wired links. When you have an RF signal, you actually have some sidebands. So there's some additional power that exists in this signal. So just in this example, this is an FM modulated signal. There's some additional power that exists in these sidebands that also has to be transferred over your PCB or possibly over a cable or a wireless link. And so what that means is that you need to ensure that the bandwidth that you need to transfer, so for example here in signal A, can be accommodated by the PCB that you're designing. So for example, if you're designing an antenna, the antenna that you're designing ideally should be able to transfer very efficiently over this entire wavelength, over this entire bandwidth. And if that antenna can transfer efficiently over this entire bandwidth, then you won't lose any of this information in the process of trying to broadcast it down to a receiver. So another important concept here is the concept of resonances. And when a resonance occurs in a structure, it is related to the wavelength. Now, typically, if you're an electronics engineer and you encounter the term resonance, it is normally in the context of like an RLC circuit. So an RLC circuit does have a resonance, and it's generally only looked at in the time domain. So it's not that that is not what a resonance is. RLC circuits do have a resonance, and it is something that you observe in a time domain measurement, like on an oscilloscope, or you can observe it like with a spectrum analyzer. However, if you have a closed structure like this, so let's just say we have a box, there are certain frequencies that will excite a resonance inside of this box. And inside that box, the electromagnetic field distribution will take a very specific distribution, and it will be very intense. And so some RF structures rely on resonances in order to support either a stationary wave inside of this box or to support propagation of a wave along one direction of this box. And so when we talk about substrate integrated waveguides towards the end of this presentation, you'll see an example of this type of structure. This same concept applies in grounded coplanar waveguides. Now, in grounded coplanar waveguides, if it's not sized correctly, if you don't apply the right sizing for that particular waveguide, then you may not be able to transfer at a specific frequency, because certain frequencies here can cancel each other. So you have very strong constructive interference between different waves. However, certain waves can also cancel each other and won't be able to transfer any power or support any kind of standing wave inside of this structure. So resonators, and when I say resonator, I mean like a structural resonator like this, are very important tools for understanding why waves can transfer through different RF structures. So those are some of the fundamental concepts. So now we're going to look at how those can be applied in board design. So when we have a PCB, generally the first place we need to start when we're doing anything with RF is with materials and designing a stack-up. Now, I had mentioned earlier that there are sometimes these design guidelines around RF PCB design out there that tell you that you should always use the smallest decay value that you can possibly get. And that's not necessarily true. If we just compare some of these values for the loss tangent and the decay value to FR4, we can see that there's really a wide range of options here for decay values and loss tangents. Now you'll notice something that is common to all of these RF materials. So these isolate materials all the way down to these different Rogers materials. You'll notice that they all have very low loss tangent. So here for FR4 it's 0.022. And then here we see it's about a factor 10 or smaller for all of these other materials. So that's really the goal with, or that's one of the main goals with material selection for RF systems, is to select materials that have very low loss at the frequency range of interest. So the next important consideration here is then, of course, the dielectric constant. Because as I mentioned earlier, the dielectric constant will determine the wavelength of the wave that you want to transfer through your PCB. So next I want to look at some stack-up examples. Now, the stack-up example that you see here, this is actually kind of inverse of what you might see for like a 4-layer PCB. So we have a 4-layer board here, and in this 4-layer board we have 2 internal plane layers, but they actually have very thin separation. So this RF, or this 4450F material, this is a Rogers material. And this particular material separates 2 plane layers by 3 mils. It's a very, very thin bond ply material. And this bond ply material essentially acts like a glue. It's like the prepreg between these 2 core materials that are on the outer layers. So we've actually built many PCBs using this particular stack-up. This was requested, of course, by a client, but this particular stack-up was used because they were doing very large structures on the top layer. And in order to create very large structures that have a 50 ohm impedance, then you need to have a very thick dielectric. And so that's why this is a 30 mil dielectric below the top layer. So this is kind of the inverse of what you would see for a typical 4-layer board. Because if you were doing like a digital 4-layer board, you wouldn't have a thick dielectric here on the outer layer. You'd actually have a thinner dielectric here on the outer layer. And then the central layer, or the central dielectric, would be very thick. So this is just an example of that type of stack-up that you can use for RF. Now, because we have 2 plane layers here, we can put RF on the top layer, and we can put very high frequency RF on the top layer. And on the bottom layer, we can then put digital if we had like a digital processor that we need to put onto this board. And then we connect everything with through holes. So this is a good example of an RF board that can support mixed signals. However, on the bottom layer, and as we'll see later with designing transmission lines, on the bottom layer you have to have some ground pour in order to balance, or in order to set the transmission line impedance to 50 ohms for any high-speed signals. So that can be challenging because here, if I fill this bottom layer with copper pour, then it creates an unbalanced stack-up. And some fabrication houses will complain that having copper pour on the bottom layer, but no copper pour on the top layer, is going to possibly warp the board. Now, I've heard debate from this from different fabrication houses. I've heard some fabrication houses tell me you always have to balance it. I've heard others say, well, if it's a small board, it doesn't matter. It's not like it's going to warp, and you're still going to have even heat distribution. So this is one of those issues where I say, contact the fabrication house that you're going to use, and then see what they can guarantee. And if they can guarantee that they can fabricate it correctly with this type of stack-up, where you have pour on the bottom layer, then you should be just fine to use this stack-up as I've shown here. So next, hybrid stack-ups. So this is one way to build an RF PCB, but you'll notice here, all of these materials are 4350B or 4450F. So these are Rogers designated materials. And if you're familiar with Rogers, you'll know that they exclusively work with RF grade materials. Now, this type of stack-up only uses 1 layer of Rogers. Now, in this particular stack-up, and we've done radar boards on this stack-up, we're only doing the RF section on the top layer. And the reason we do that is because this Rogers layer up between the top signal and then the ground on layer 2 is very low loss. And so any high frequency signals can be routed up on this top signal layer. Then the internal layers are power, signal, ground, and then on the bottom we have another signal layer. So this is another example where we can have digital on the bottom side, and that's because we're blocking all of this digital stuff from the RF stuff on the top side. Now, in this particular stack-up, I have a signal layer here below the power layer, and this signal layer could be used for other digital things. So it could be used for lower speed digital, maybe it could be used for some control lines. There are all sorts of different options. But the high speed signals, maybe like Ethernet or USB or something like this, should be on this bottom signal layer. Now, if you had to support a lot of high-speed signals, you may want to actually re-engineer this so that you have the thick core layer, and then you have a thin layer between the ground on L2 and then the power on L3. And so if you make this this region much thinner and then have the thick core in the middle, that's actually beneficial for power integrity. And that's something that you are going to need more of when you have a lot of digital signals operating in the PCB. So that's a bit of a topic for another webinar on power integrity. It's a bit more of an involved topic, so we won't go too deep into it. But just remember, as you pack more and more very fast digital signals onto this board, you would need to bring power closer to ground to provide enough decoupling and capacitance. So I like this stack up as well, because this particular stack up was used in a recent project also for a radar system. Now, this particular stack up was used, number one, because it was already validated in a reference design. So there's actually a lot of value in doing that. But the other reason that this stack up is used is, as you can see here, in these top 3 layers, we have very high frequency. So these are our radar signals up on the top layer. L2 is all ground. Now it's defined as a signal layer, but it was used as a plane. And then on L3, we have 20 gigahertz. So we have a lower frequency signals being routed here on layer 3. Now in layer 3, where we have this 20 gigahertz signal, this low frequency oscillator is used to synchronize multiple transceivers on the top layer. And so there was a lot of 20 gigahertz routing on this board, and because of that, we needed to have 20 gigahertz on its own layer. And then you notice that we shield that 20 gigahertz layer from the other layers using these ground regions. Then we're able to have power and lower speed signals on layer 5. And again, we have this plane very close to layer 4 so that we have good decoupling. And then we have the high speed signals on L6. And then there's additional 77 gigahertz routing on the back side. And so doing this in this way allows us to interleave ground in between all of these different layers. And the reason that's done is so that these different types of signals are fully shielded from each other. Now, there's an important point to note here, which is reliability of hybrid stackups. So hybrid stackups can have a problem if the PCB fabrication house does not know the best practices for working with them, or has not optimized their process for working with these types of stackups. So in this type of stackup, where we have a PTFE layer, so this would be like your Rogers layer, above an FR4 layer, there's a potential for the whole wall plating in a drilled via hole to be very thin, and it could potentially crack, as you can kind of see here on the right side of the screen. So this happens during the de-smear process. So when this hole gets drilled, when it gets mechanically drilled, what happens is they use a process called plasma etching, where essentially a gas is superheated and that gas ionizes, and it's able to infiltrate these holes. And in the process of doing that, it removes any of the debris that is in these holes. Well, the problem with that is that it actually etches the FR4 layer, meaning it creates, or it removes more of this FR4 material. So if this etching rate were uniform across the entire hole wall, then that would be fine. That's not a problem. But however, it's not uniform, and you can clearly see that in this image here. And so the result is that you can get insufficient hole plating in the FR4 region, and this can create an uneven surface and possibly a cracked surface. So the next thing to consider in fiberglass epoxy resin substrates is the fiber weave effect. And so this is often brought up in the context of differential pair routing. And it is true that it is important in differential pair routing. And the reason it's true is because these different regions in this material or in this substrate have different dielectric constants. And so what that means is that waves traveling along, let's say, this top trace will have a different velocity in these black regions versus in the glass region. So these black regions are the epoxy resin filler, and then the gray region is your fiberglass that makes up your PCB substrate. Now contrast this with the lower trace. The lower trace has no skew compared to the top trace because the dielectric constant in its nearby this trace is more or less uniform. And so the result of this, when you measure this on a TDR, so a time domain reflectometry measurement, is that this there is some variation in the impedance that can be measured or in this case simulated. So in this particular example, this was simulated with Symbior, and the result is this very wavy behavior in that it appears that there's a lot of impedance variation along this trace. And it is true, there is a lot of impedance variation along this trace. And when you have some impedance variation, you also have propagation constant variation, meaning you have velocity variation along this trace. And so that's why you get skew in the differential signal between these two traces. Now, with an RF signal, we actually do care about skew, but it's particularly in the case like on this board where we had to use the 20 gigahertz signal as a clock. And this 20 gigahertz signal being used as a clock means that you need to have zero skew no matter where that 20 gigahertz signal is routed in order for multiple transceivers to be synchronized. And so I'll show an example of that type of system later. But this essentially means that we would prefer to use a tighter glass weave. And this tighter glass weave, the 7628 weave in a fiberglass epoxy resin substrate, will have much less variation in the dielectric constant along the length of the material. Now, another thing that can happen is at very high frequencies in these very loose weave materials, there can be something called periodic loading, which actually causes these big peaks in the return loss spectrum. And so in other words, what it means is that the return loss spectrum is showing a lot of reflection. So there can be a lot of reflection at certain points along this trace because you are exciting resonances in this structure. So the resonance occurs when you have a half wavelength resonance here, and that half wavelength resonance builds up to very high amplitude, and as a result, you would then get a problem with very strong electromagnetic wave being built up here, and it would appear as if you have very large reflections traveling backwards along a trace that passes over these voids. So this is another reason to use a very tight weave. So the next thing I want to look at is the type of copper that is used in these materials. So copper foils can be are typically manufactured in these large rolls, and you can see here on the left an example of a copper foil. So it's manufactured on this very large roller. It's supplied in a roll up to a desired thickness, and then a downstream manufacturer will take that copper, they'll cut it off of the roll, they'll put it onto the other material that they're using, and then that's how they will fabricate PCB substrates. So I'm simplifying it a little bit, but you kind of get the idea. They take this copper and then they put it onto a glass resin substrate. Next, what they sometimes do is they will pass it through some surface treatments. So there are surface treatments that can be used to treat this copper and modify its properties. Then there's another process that can be done with these copper foils, which is to put it through a pair of rollers and anneal it. So it can be the copper can be heated up and rolled. And all of these different processes will affect the roughness profile of this copper. So the roughness profile is something that's very important for determining the impedance of a transmission line that is built on one of these PCB substrates. So the impedance of that transmission line depends on the roughness profile. So these are some typical values for roughnesses that you will see for different types of copper. So the process will determine the roughness profile. Now, if you look at some data sheets, you can't be sure that they're actually going to tell you the value of roughness in the data sheet. Now, on the left, we have an example from Rogers' 3000 series datasheet. Now, this particular table tells you the process that they use to produce that copper, but they haven't told you what the roughness is. Now, you can actually get that data from Rogers. They'll tell it to you if you ask them. So, just send them an email or something like this. But they can get that data for you. But it's not found in the data sheet. Now, here on the right, we have something from AGC to Conic. So this is a different laminate supplier or a different laminate material here. And this particular material, they actually do show the roughness values, and they give them in microns and microinches. So here you can actually use this to select the right type of copper that will then affect the losses that you see on your particular interconnect. Now, if you actually look at a microscope image of electrodeposited or rolled copper, they're actually very easy to identify from an SEM image. So these are only 5,000 times magnified scanning electron microscope images in the SE mode. So from here, you could actually use image analysis to determine what the roughness is. And just as an example here, this data from Rogers, so from John Coonrod, he actually has extracted the surface roughness value, and he can, very clearly see why you have roughness. So the electrodeposited copper, when it is electrodeposited, it accumulates in these big clumps. And so you have these little particles that make up these larger clumps on the surface of the copper foil. And that is what gives you this roughness profile. Now, in the rolled anneal copper, you can actually see these horizontal striations. And so the rolling direction here for this particular type of copper is vertical. So this is where the rolling direction is, just from looking at this. And you can see here, this measured surface roughness is actually much smaller, even though they have the exact same magnification. So the magnification, you can see right down here in the lower right corner of these images. Magnification for these two images is the same. Rolled anneal copper has much lower roughness. Now, so how else can you determine this without image analysis? If you have an AFM, so an atomic force microscope, you can do a profilometry measurement. And then there are also interferometric measurements that can be done. So this is an optical measurement. Now, the effect of copper roughness is to modify the dielectric constant that is experienced by a signal that is traveling between these two conductor regions. So in a real conductor on a PCB substrate, there will be some roughness, and this roughness profile will then cause the dielectric constant to be different than the real dielectric constant. So here, epsilon as a function of frequency is the real dielectric constant, and then the nominal thickness of the dielectric minus this roughness profile correction gives you the effective dielectric constant. And you take that, and that modifies the capacitance of any interconnect that you create with this particular copper. And then when the interconnect changes, or the interconnect capacitance changes, that causes the impedance to change. Now, there's another effect here that changes the impedance, and that is the skin effect. So the skin effect is increased, meaning the resistance due to the skin effect is increased due to the roughness of this of these copper materials. And so there are some different models that are used to describe this K of omega function. So if you're using like Altium Designer, it actually includes a roughness correction tool in it. Other tools like Symbior, they also include some of the, or they include a roughness correction tool in their simulator. Or you can do it by hand, and there are different models that you can actually use to calculate the roughness correction factor by hand. So essentially, the function of this roughness correction factor is then to multiply onto the skin effect resistance. The skin effect resistance you can get from online calculators, and it increases the skin effect resistance. So you can actually see what the effect is in terms of the losses and the decay effective value for measurements. So these, this on the left is value from a data sheet compared with a roughness measurement that was done, I believe, by Bert Simonovich. And he actually was able to validate these particular expressions using this data. And so you can see very clearly that there's an increase in the dielectric constant. So this also means that the wave is slowed down a little bit, because when we increase that dielectric constant, we decrease the velocity of that wave just a bit. The other thing that happens is we get more loss. So when we increase the skin effect, we get more losses. And so here we have two microstrips, all fabricated to the same impedance, on the same material, with the same thickness. And at very low frequencies, so in the Wi-Fi range, you can actually see that these two curves overlap. So there's really not a lot of difference in the loss profile at low frequencies, such as you might deal with in Wi-Fi or Bluetooth, or maybe like an IoT protocol or sub-gigahertz radio. So all of those, the copper roughness doesn't matter. But when you're out here at, let's say, short-range radar, or you're at 24 gigahertz radar, now you can very clearly see that there's a big difference in the losses. And the losses get even worse when you're at much higher frequencies. So when you're here at at 77 gigahertz radar, now you have very big differences in the losses. And so when you're working in this range, you actually do want to get that copper surface roughness as low as possible. But when you're at these lower frequencies, it doesn't really matter. You can use whatever the material vendor supplies you. So the next thing I want to look at is platings. So surface platings are very important in RF PCBs. And actually, let me just skip ahead for a moment. The reason surface platings are important in RF PCBs is because we remove the solder mask. And the reason we like to remove the solder mask from emitters and from waveguides in an RF PCB is because the solder mask can have a pretty high loss factor here. So the solder mask is actually very lossy, and we would like to eliminate that loss in an RF PCB. And so that means removing the solder mask. And you can see that here in this little filter board. So this filter board operates at 5.8 gigahertz, and we pulled off the solder mask to reduce all of the losses. We have a couple of passive filters here. And then you can see here we have some very tiny inductors here. So this particular board, having all the solder mask pulled off, eliminates this source of loss. But because the solder mask is pulled off, we need to ensure that all of this copper is protected and that it doesn't oxidize over time. So to do that, we apply a surface plating. And so even though you don't see it in this example from Altium Designer, when it's fabricated, it will have surface plating. And this particular design was fabricated with silver surface plating. So it didn't actually appear kind of this gold color like you see in the 3D image. So one of the reasons we went with silver is because if you actually look at the loss profile versus frequency, it's that if we were to use a, let's say, immersion silver compared to solder mask, you can see that the immersion silver plating has much less loss compared to the solder mask. So SM here in this right graph is solder mask. Another option is OSP, which is organic solderability preserve. This particular material only has very low shelf life. So if you're going to use OSP, you need to use it quickly because that will eventually degrade, and then you won't have a surface that is so easy to solder to. And those two surface platings have roughness or incur losses that are comparable to the bare copper. So what that means is that these two materials do not make the copper more rough during the plating process. Now, if you're using a plating that includes nickel, these nickel-based platings can have a lot of problems with roughness. So the examples here are NPIG and ENIC. So these two surface platings are actually much less desirable for RF systems. And this is because they need to deposit this seed layer of nickel in order to cause a gold film to then adhere to the surface of this interconnect. And so that actually ends up increasing the roughness. Another option is HASL, HASL, and it's going to be somewhere in this region. It's actually going to be somewhat rougher than OSP and immersion silver. So these two are really superior for RF. So if you're going to be using surface platings, it's important to know the frequency range where these start to matter. And so again, you can see here that when we're below 5 gigahertz, maybe we're at the 2.4 gigahertz region, so we're operating in an ISM band. The surface plating doesn't really matter very much. It's a very small difference in the loss profile. Now, when we get up to 5 gigahertz, we can start to see a big difference. Now, 5 gigahertz is right where you're getting into the Wi-Fi region, particularly Wi-Fi 5 region. So in this region, you can actually see a big difference. But it's not going to be a kind of thing that ruins your design. Just because you use ENIG, yes, there's going to be less loss, but the design is still going to work. It's once you get out here into these much higher frequency ranges, so 24 or 25 gigahertz, where you start getting into radar, now it really matters a lot. And you can see there's a really big difference here. It's a half a decibel. Well, that half a decibel of loss per inch can really limit your routing lengths in these designs. And it gets even worse as you get out to higher frequencies, as you can clearly see from the graph. So next, one option to try and protect, let's say, the copper or let's say an immersion silver PCB, let's say from tarnishing or from degrading, is to apply a conformal coating. And so it is true that conformal coatings can be very useful. They can protect a design from environmental degradation. So that degradation could come from humidity, and it could come from high temperatures, could come from exposure to noxious chemicals, so like a corrosive agent that might exist in the air, or as a liquid. So conformal coatings are very useful, especially in high reliability PCBs. And so they are something that is important to consider if you're building something that's going to work in one of those areas. However, the problem with conformal coatings and RF designs is that in these designs, they can very strongly absorb at gigahertz frequencies. So at these very high frequencies, they can absorb very strongly. And they're useful in one sense, in that if I were to take a conformal coating, so like a polyurethane-based conformal coating, it comes in a spray can, and I was to mask my PCB and just spray that conformal coating along the edge of the PCB, what that's going to do is it's actually going to suppress emission of radiated electromagnetic waves. So it's going to absorb that radiation before it can leave the edges of the PCB and then travel and interfere with something else. And so you can actually see the very sizable reduction that you get. And it's almost a factor of 10 reduction. Actually, that's more like a factor of 4 reduction, but still really good reduction in the emitted radiation profile at 10 gigahertz. So if you're operating, again, in the Wi-Fi ranges, and you know that your design needs to have high reliability, and there is a possibility that it is going to be exposed to some noxious chemicals. If you're operating at low enough frequencies, conformal coatings are still a possible material that you can use to protect the design without ruining signal integrity and without ruining the ability to broadcast signals. However, once you get into the millimeter wave, again, this is not going to be desirable. And in the millimeter wave, we would instead use enclosure-based shielding. So we're not absorbing directly on the PCB. The reason we don't want to put that absorbing material on the PCB when we're operating at millimeter wave frequencies is because it's going to absorb the signal as it's still on the interconnect. So you could actually lose the signal in between a transmitter and a receiver on the PCB. It's better to block it at the enclosure level, so that way noise is still being generated by the PCB, it's just not leaving the enclosure. So that's where enclosure level shielding becomes important. Excuse me just a moment while I get some water. Okay, so that finishes our second section. These are really the core design concepts that are needed to understand RF PCBs at a deep level and to actually build a physical board that you can then assemble and use in a real application. So we've covered the bare board portion of this, but now what I want to look at is interconnect design and routing. And so when we say interconnect design, the biggest piece of that in a printed circuit board is really two things. The first is the transmission line, and then the second is the vias. Now, I'm not going to cover the vias in this section. The reason is that oftentimes you will see a recommendation that you should never use vias on RF signals. I'm going to show you an application later where you actually have to use vias. You really don't have a choice. You absolutely have to use vias in order to make this application work. For now, we'll focus on the transmission line design portion, and then we can get a little bit deeper into the application areas later. So generally, if you're working with RF signals or an RF system, and you see any kind of signal integrity guidelines, or you see any kind of component specifications, if they're operating on a PCB, they're generally going to be specified at exactly 50 ohms. So there will be a requirement in the design to design transmission lines to 50 ohm impedance, unless the component data sheet or some other system specification dictates otherwise. So I think it's interesting to ask, why do we care about 50 ohms? What's the important value, or what's the importance of a 50 ohm impedance in these systems? So the reason for using a 50 ohm impedance is actually finding a balance between what happens in coax cables. So these guidelines were originally developed based on signal propagation in coaxial cables that were either air-filled or PTFE filled. So in a dielectric filled coaxial cable, you get maximum power transfer below a certain mode excitation at 30 ohms, and that is shown here in the red portion of this graph. Or you can get the lowest losses when the impedance was 77 ohms. So this might be a little counterintuitive, but it's really about adjusting the inductive and capacitive contributions to the impedance in a coax cable. Now, of course, this is when epsilon r, or the dielectric constant in that coaxial cable, is equal to 1. Now, it just turns out if you take that coaxial cable and you fill it with PTFE, so this is the same material used in like Rogers or Arlon substrates, when you fill that coaxial cable with that material, it just so happens you get the lowest loss right at 50 ohms. So it's not exactly at 50 ohms, but it's close enough. And so, of course, we just settle on 50 ohms. Now, 50 ohms is also kind of a nice balance between reasonably low attenuation and reasonably high maximum power capacity in these particular coaxial cables. And so because we want to have impedance matching when we're connecting different types of components together to form an interconnect, if we have 50 ohms as the desired impedance in PTFE-filled coax cables, then we also need to use 50 ohms on the PCB and on connectors to ensure that we have zero reflections at the interface between each of those different elements in the system. So that 50 ohms value is enforced for that reason. So we could have settled on 60 ohms, just as an example. We could have settled on 77. There are all sorts of other values that you can use. But based on the available coaxial cables when this kind of guideline was being developed, as it turns out, it's best to just use everything at 50 ohms. So next I want to look at the transmission line styles. I'm sure anyone who has used a PCB design program or has used a impedance calculator to design like a high-speed PCB has seen all of these different structures that I have shown here on the left side of the screen. So here on the left side, coplanar and microstrip lines are preferred for RF. And there's an important reason for that. Here in these two particular transmission line geometries, what we have is when the signal is traveling between these two conductors, so when it is traveling on this interconnect, the electric field and the magnetic field exists around this trace. So the signal doesn't really travel on the conductor. The signal is bounded by the conductor, and the current that exists on the conductor generates an electromagnetic field around this trace. So some of those field lines pass through air in these geometries. So let's just say you see here where my mouse is. If I have current, let's say that exists on the top surface of this coplanar microstrip, there will be electric field lines that pass through air and then terminate at the nearby ground. Now, there are also field lines that pass through the substrate material and terminate at the nearby ground. But because some of those field lines pass through air, the result is that those field lines experience lower losses. So less of the signal is lost as it travels on a microstrip line or a coplanar line compared to strip lines. Now, you can still do strip lines in RF boards. You can still use strip lines. You'll have the same thing, right? The electromagnetic field is going to exist around this conductor that carries the signal. Now, the issue here is that, of course, the field lines are going to span from this conductor to the nearby ground. But because they all exist inside the dielectric, then it sees all of the possible loss that you can see from this dielectric material. So this is the reason that strip line is less desired for RF routing. However, as I showed before or mentioned before in the 8-layer stackup I showed earlier, you can do strip line routing for RF signals. And in fact, we were doing it at 20 gigahertz. So that just illustrates that, yes, you can in fact do this. Now, if you're working with a coplanar arrangement, it's not just a coplanar microstrip that you would want to use. You would actually want to use a coplanar waveguide where you have ground on the next layer. And in particular, you would like to use a grounded coplanar waveguide. Now, the grounded coplanar waveguide essentially takes this arrangement, and then we lay out vias along the length of the conductor. So these vias are attached to ground pore on the top layer. So the ground pore was omitted just for clarity, but you can see it from the side view that there is some ground pore that is being attached to this nearby plane through these vias. And so the distance between these vias will determine the propagation behavior of this particular interconnect. Now, again, with coplanar waveguide design, there is this guideline that says whatever your wavelength is or whatever your signal wavelength is in this structure, the width needs to be less than that. So essentially, if you draw out a portion of the wavelength, it spans larger than the size of this cavity. Now, you can probably guess why that is. The reason for that is to prevent any kind of resonance that might build up in this cavity and then cause a very high impedance that then creates reflections along this interconnect. So this is another instance where resonances are very important to understand. As long as this width is less than the wavelength, or half the wavelength, I should say, of your signal, then you can prevent those resonances. But eventually, the signal frequency gets so high and the wavelength gets so small that you can no longer do this reliably. And the reason for that is because, number one, manufacturing considerations, right? I can't keep making this grounded coplanar waveguide smaller and smaller and smaller as my frequency gets larger and larger. So there are other things that I have to do to ensure that I can allow signal propagation at my desired frequency. And I'll show you exactly what I mean later when we look at grounded coplanar waveguide design. The other issue here, the other reason that you can't just keep making this structure smaller and smaller is because you have an impedance target that you have to hit. So remember, we want to be working at 50 ohms impedance. Well, the reason we need to consider the geometry here is that eventually, if we continue to make this smaller and smaller, we might not hit our 50 ohm impedance target. So you have to balance both of those issues of, number one, preventing resonances, but number two, also ensuring that you hit an impedance target. The other thing that I need to mention here is the distance between these vias. So here in the lower right portion of the screen, you can see the distance between these vias. This distance also needs to be appreciably small. Okay, so when we say lambda over 8 here, that's an eighth of the wavelength. So it's a good idea to keep this spacing between vias less than an eighth of a wavelength. And the reason for that is because this structure will look like a totally closed cavity if you manage to do that. So it's going to have very good containment of the electric field and the magnetic field, and ideally that will prevent leakage of the field from the edges here. However, you have the same problem with what happens at much higher frequencies. Eventually, the frequency gets so high that the distance between these drill centers becomes so small that now you can't manufacture it with standard processes. So at that point, you then need to either use an alternative process like HDI. Maybe you can get those vias packed closer, and we'll see an example of that as well in just a little bit. Or what you have to do is, in making these two vias closer spaced together, you can actually add another row but stagger it. So you'd have a via right here and then a via right here, and so on and so forth down the length of this. And so that's another way that you could try and pack more vias into this smaller space, and then ensure that you still get the required level of shielding and isolation for the electromagnetic field inside of this structure. Okay, so next, fundamental theory of transmission lines. So transmission line theory uses a particular model called the RLCG model. Now, the RLCG model is derived from first principles, meaning you can derive it from the wave equation. And so if you take engineering classes, they generally won't show you what each of these particular symbols, the R and the L and the C and the G, are defined as. So here, this omega is just the angular frequency. That's 2 pi divided by the t, or the period, for our electromagnetic wave, or 2 pi times the frequency, and that gives us our omega. So we know what that is, but this R and L and G and C need to be explained, okay? So the R is the resistance. This is the DC resistance plus the contribution from the skin effect. So the skin effect creates some additional resistance in this particular structure. Next, the inductance also depends on the skin effect. So there's an inductance at infinite frequency term, and this is generally what a calculator application is going to give you. So like if you go on the internet and you find a calculator application that can give you the inductance of this of your transmission line, it will give you this L infinity value. However, there are other transmission line calculators or skin effect calculators that can then return a skin effect value, and then you will know what the skin effect is. And so the reason I say that this is incomplete is because it does depend on the geometry of the transmission line. So for example, the skin effect resistance is going to be different for a coplanar line than it is for a microstrip line. Next, we have the G term, which is a substrate loss term. And this is where the loss tangent comes in. So if you know the loss tangent, you can calculate the G value. You also need the capacitance. Now, this capacitance is defined by the material properties. And then there's this K sub G term. So this K sub G term accounts for fringing capacitance. So it accounts for the fact that the electric field lines in this microstrip line don't just pass from here, this bottom surface, directly to the ground plane. They actually pass kind of in these curves along the edges here, okay? And that is called fringing capacitance. So that fringing factor, the K sub G, could be anywhere from about 3.5 to 4, I believe, for microstrips, and it's going to be similar value for strip lines. We also need some of these material parameters, right? So we need to know the dielectric constant, and then once we know the copper roughness, we can just take our RS and then multiply it by our copper roughness, and that gives us everything we need to know in our transmission line. Now, you could, in principle, do this by hand if you want to, and I think, being a physics person, having done this for many years, I think it's an important exercise to at least do it a few times and know how to do it. However, for ease of engineering and to just speed up your design process, it's important to also know how to use these calculators, because there are calculators that can incorporate these different parameters for you and give you a transmission line impedance. So there are also several formulas that you can use, and I think it's very important to have the context behind these formulas. Now, these formulas were developed from several different sources. So hold on just a moment. So the first source for some of these impedance formulas is the IPC 2141 formula. Okay, so this particular formula was developed using data measured from many different 50 ohm transmission lines. So what that means is that this particular model is only valid for 50 ohm transmission lines. So if you try to use this to determine H and W and T, so H is the height above the substrate, W is the width of the trace, and T is the thickness. If you were to try and use this to determine, let's say, a 30 ohm trace, your values will not be accurate. They can actually be very inaccurate. The other reason that this formula is inaccurate is because it doesn't include anything about the loss tangent. So it only includes the real part of the dielectric constant, but nothing with the loss tangent. And then, of course, there's no way to account for the skin effect. Now, Waddell's equations are more accurate. And they're more accurate because they are not developed based on measurements of 50 ohm transmission lines. They're actually derived directly from Maxwell's equations. And that is the thing that makes them much more accurate. And so they're much more accurate until mode excitation occurs. And so I'll explain what that is later. But just know that as long as you're at mid-range frequencies where you haven't excited any sort of cavity mode like inside of this grounded coplanar waveguide, then Waddell's equations are going to be very accurate. So I'm only showing here the equations for the microstrip line. However, Waddell's textbook has transmission line impedance equations for a huge range of different structures. And I mean, if you think of a transmission line that you can put on a PCB, Waddell has an equation for it. Now, those equations can be very difficult to work with because they can involve elliptical integrals, and those elliptical integrals are something that I've never solved by hand. It's something that I should know more about, so I'll admit it's something I have to study. But elliptical integrals are something that you would normally evaluate numerically. And so this is another reason why for certain transmission lines, including like this grounded coplanar waveguide, it is better to use a calculator application or your layer stack manager. So like in Altium Designer, you can actually calculate the impedance for like this coplanar waveguide, which would be very difficult to do by hand. Now you can do it by hand, it's just that I think it involves, 70 equations in order to calculate it. So it's a huge number of equations. Strip lines. We also have the same thing with strip lines. So we have a formula from the IPC 2141 standard, and again, known to be inaccurate outside of a 50 ohm range. So you can use this to get reasonably accurate results up into the gigahertz frequencies, so low gigahertz, if you're only working with 50 ohm transmission lines. And so when I say you're only working with 50 ohm transmission lines, well, what you do is you pick two of these parameters, and then you solve for the third parameter based on your target impedance of 50 ohms, and you'll get a reasonably accurate result. Waddell's equations also highly accurate, and they are also much more detailed, but you can use them to get accurate results outside of this 50 ohm range, just like we had for microstrips. So the next thing I want to do is to maybe compare what the typical width is for strip lines versus microstrips. This normally comes up in the context of HDI, where you need to pack a lot of traces onto a very small area. And as a result, you would then need to determine what is the maximum width that you can use in order to hit a target impedance, especially in like a high-speed HDI design. But in an RF design, the strip lines can still be used. It's just important to note that they're always going to be thinner for a given DK value. So if I use the same DK value, same layer thickness, and I try to calculate the width of a strip line versus the width of a microstrip, the strip line is always going to be thinner, okay? And it doesn't matter what the frequency range is, what the target impedance is, the strip line is always going to be thinner. Same thing with the input impedance. So the input impedance applies the same type of modification to the impedance experienced by a signal, regardless of whether we're looking at a microstrip or a transmission line. So I bring up the input impedance because the input impedance is generally what you're matching to when you determine impedance matching. So when we say impedance matching, this is what I was referring to earlier, where when we're using the system impedance, we want to make sure everything has the same impedance from our transmission line to our vias, to our connectors, to any cables, and then the inputs on any components. So all of those different elements, all 5 of those elements, we would like to make sure that they are matched to the same impedance. So you can adjust the input impedance with the width, but it's the same type of modification that occurs regardless of whether we're working with a strip line or a microstrip. And so the result here that you can see is that the strip line and microstrip can have very different widths for the same impedance. Here you've got almost a factor 3 larger microstrip compared to the strip line. So if you're routing with microstrips, just note that if your calculator tells you you need to have a very wide microstrip, then it's probably not incorrect. So just make sure you understand that when you're using calculator applications to design transmission lines. So this is a strip line problem that I always like to show on these types of webinars, just to give some kind of example for what you can expect when you're designing to a 50 ohm target impedance. And in this example, we're looking at a strip line that is being used to connect a 50 ohm source. So we have a 50 ohm component on our source end of our interconnect that is connected to our 50 ohm target impedance transmission line. And then at the load, we have 1 picofarad load capacitance. So this is important because CMOS-based components have capacitive inputs. And what I mean by that is even if you terminate that input on a component to 50 ohms, there is still some load capacitance, and so that capacitance will cause the input impedance of your receiving component to look like much less than 50 ohms at very high frequencies. So that 1 picofarad load capacitance in this example will actually create some deviation in the impedance, and we'll see what that looks like on S parameters here in just a moment. And then here I have some values for a Lorentzian model for the dielectric constant. Just note that the datasheet value for the dielectric constant in this example is 4.14. So this is an isola material. But there's a method here in this journal that actually provides these different values that you can use in a Lorentzian model for getting the dielectric constant as a function of frequency. So this is a topic for a future webinar. I think it's definitely important to know because it tells you how simulation programs work. But this is something that I won't get into further in this particular webinar. Instead, let's go ahead and look at what the impedance profile looks like for a transmission line. So even though we are designing to a target impedance of 50 ohms, we don't actually get 50 ohms. The reason we don't get 50 ohms is, number one, first of all, the transmission line has a complex part of your dielectric constant. Okay, so because the dielectric constant has an imaginary part here, what that means is that the impedance will also be a complex number, and it has an imaginary part. So if we go back here to this example, you'll notice here we have these I terms here in this fraction. This is what's going to tell you that the impedance will end up being a complex number. And then we only really get to 50 ohms just somewhat for this smooth line. It's actually just a little bit below. Once you start accounting for roughness and you account for dispersion, what you end up getting is these kind of curve profiles that tell you what exactly the impedance is, both for the real part and then the imaginary parts. So what we can see here is that when we consider the skin effect resistance, when we compare these two for the rough versus the smooth, what we see is that the roughness does provide an increase in the impedance compared to the smooth line. Now, it also creates an increase in losses, and we can see those losses in the S parameter data. Now, first thing that we see, on the left, we have some S parameter data here from 0.1 to 10 gigahertz. So here in this kind of mid-range portion of the right side of the graph, this is the region you would be operating in if you were dealing with like an ISM band or Wi-Fi or Bluetooth. So these curves are still actually very good. Now, the S11 S parameter tells you how much power is reflected. Okay, so this is a measure of reflected power. We see that there's very different results here with our 1 picofarad load capacitance. We have parallel termination exactly at 50 ohms, but we still get these reflections at different frequencies. Now, ideally, these reflections will be very low on the graph, and that's what we want to see. We'd like to have this curve be as low as possible, so as big of a negative number as possible, and that's desirable with reflection with S11s. Now, this S21 curve, we'd like it to be up high as possible. We'd like to be very high. So here, when we can add in the roughness, and when we use the incorrect width in a rough transmission line, what we see is that the roughness increases these losses, and they start to increase very quickly. Now, the important point to note here is that your solver, or most solvers, I should say, are not actually predicting this S21 profile. So this is something that you need to calculate by hand, or you have to use maybe a more advanced solver to simulate this S21 curve. So I'm going to show you an example of how to calculate this by hand in just a moment. But just important to note that if you're using a calculator application, it may not actually calculate this attenuation for you. Okay, so copper roughness. When is it too rough? This is an important question here, okay? Excuse me. So here we have a total attenuation that is given by the sum of our conductor attenuation and our dielectric. And this is generally specified in decibels per length. So this decibel per length value is important here. Now, normally this C, which is our transmission line capacitance, this is going to be in ohms per length. Okay, and your length value could be, per inch. You'll actually notice here in a lot of these graphs, I use decibels per inch. Part of the reason for that is because I'm in the US and everybody else uses inches, so we use decibels per inch. But you could do it in decibels per centimeter or decibels per meter, just as an example. So here in these formulas, we also have a term for the conductor loss. Now, the conductor loss is where you start to see the roughness correction factor and then the skin resistance. So these roughness correction factors, you can calculate that by hand. If you look in the reference that I showed earlier. So when you take a look at these slides later, you'll be able to find that reference, and then you can calculate this by hand if you want. Now, what I've done here for this conductor is I've calculated a skin effect just nominally for this particular example that we have earlier. Okay, so this is skin resistance for these two different types of conductors per unit meter. Now, when you plug in the DC resistance for your line, you plug in the target impedance of 50 ohms, you plug in the loss tangent, we're now able to compare what happens with the dielectric loss, the smooth conductor loss, and then the rough conductor loss for different roughness models. Okay. Now, here with the dielectric, we see that it is actually much larger at these higher frequencies compared to the conductor loss. The reason for that is because we can see here the conductor loss is proportional to the square root of frequency, but the dielectric loss is proportional linearly to the frequency. Okay, so if I double the frequency here, I double my dielectric losses. Here, if I were to double my frequency for the conductor loss, well, then I wouldn't get double the conductor loss. I would get about 1.4 factor higher conductor loss. So what you see initially is that at low frequencies, the conductor loss can be substantial, and it can exceed the dielectric loss. But eventually, the dielectric loss becomes the dominant loss mechanism. Now, even though the dielectric loss is dominant, that doesn't mean that the conductor loss is insignificant. The conductor loss is still significant, and we can see that very clearly here when we compare what's going on at 10 gigahertz for the dielectric loss versus the conductor loss. So this is another motivator to use as smooth copper as possible. Now, as you use a smoother copper, that's going to cause this K value to be smaller. So the smoothness of the copper does not change R sub S, which is your skin resistance. It only changes this roughness correction term here. So this is the final section. This fourth section will focus on some RF structures and components. And when I say components, I'm really talking about printed components. So the type of RF structure that you might design out of copper that will then be etched into a printed circuit board. So I mentioned earlier about coplanar waveguides. So I want to look at coplanar waveguides because they are very important at really at all frequencies. Now, if you're operating, let's say, at Wi-Fi frequencies, you have to make this coplanar waveguide very big in order to excite a specific mode inside of this structure. And when I say excite a mode, I mean create a standing wave inside of this structure. And what does very big mean? Well, very big means a couple dozen millimeters. So it needs to get very large in order for this structure to have a large enough span between these vias in order to excite any kind of mode structure in here. So if you're operating Wi-Fi frequencies, the main reason that you use a coplanar waveguide is because it gives you some shielding with respect to other circuits in the system. So if you look at any system that uses Wi-Fi and it has to route a signal into an antenna, there's going to be other stuff on those boards. There will be some kind of embedded processor. There might be some kind of DSP, some kind of application processor or something like this. So those are going to exist somewhere on the board. And you need to make sure that you shield your RF frequencies from those other portions of the system. However, when you're operating at let's say very high frequencies, like maybe it's SATCOM or maybe it's radar, now it's actually possible for the width to be much larger than half a wavelength. And so you can't just keep decreasing the size, as I mentioned earlier. So what happens when you're in this situation, so the MSTL situation where you have the width larger than half a wavelength? Well, what happens is you can excite these electric field distributions. So at really low frequency, here on the top left, what we're showing is the electric field in the Y direction. So this is one electric field component. And you can see here that the electric field, and as a result the magnetic field, are all very uniformly distributed along the length of a coplanar waveguide. Okay, so this is what happens at very low frequencies. But at very high frequencies, we can excite an electric field distribution that looks something like this. And this is where we have these very nice, very well-defined regions of electromagnetic energy that are being excited and resonate inside of this structure. So these field distributions along the length and width of this structure are called eigenmodes. So if you take a differential equations class or particularly a partial differential equations class, if you take a partial differential equations class at university or you read maybe a textbook, you will see reference to this term eigenmode. These are fundamental solutions of the wave equation, and they refer to these field distributions in an electromagnetic system. Same thing happens in acoustics, in vibration mechanics, these other areas of math and engineering. So what happens in terms of the losses and the S parameters? Well, this is very important here. Now, here, when we have the structure very large, what happens is that we can only operate at lower frequencies without creating very large losses at very specific frequencies. So let's just say, for an example, we wanted to operate a particular coplanar waveguide with VL equal 2700 micrometers or 2.7 millimeters. So remember, just for a moment, VL is this distance from the trace over here to this via, okay? So in that case, where VL is approximately this wavelength associated with this frequency divided by 4, what we end up seeing is right at that frequency, we have very strong loss. So we would not be able to operate this particular grounded coplanar waveguide at this particular frequency. And then you can see here that there are these other frequencies that start to arise in this structure where you get very strong loss. And they just repeat over and over again technically up to infinite frequencies. But if you continue making this structure smaller, meaning I take VL and I bring it closer and closer in to the edge of the trace, what happens is that now you are pushing those frequencies where you see strong loss up to higher values. And in fact, here in the red curve where you have this 0.4 millimeter distance between the trace center and the via center, you actually don't see any resonances up to very high frequencies. Now, this value here, 0.4 millimeters, is kind of special because you're actually going to run right up against the edge of what you can reliably manufacture. So you can get up to 100 gigahertz or a higher operating range, and you can definitely use this type of structure for radar, because at radar you'll kind of be in this range where my mouse is, so between 70 and 80. But you won't be able to use it once you get in well above the 100 gigahertz range. We have the same kind of results for the via pitch. So when the via pitch gets very small, we also push those resonances up to higher and higher frequency multiples. But when the via pitch is large, now there are some resonances that we can excite, and those resonances will then also cause very strong loss at specific frequencies. And so we essentially are destroying the signal if we're putting it through this particular structure and it has this specific frequency. So the takeaway here is this. This grounded coplanar waveguide can only transmit certain frequencies where these S21 curves have very low value or are very close to zero. When you get to these very strong lossy peaks here at higher frequencies, this structure can no longer support these very high frequencies, and it will destroy those frequencies, and that power will not reach the other end of the interconnect. So this is kind of summarized by looking at a power loss value. Okay, here is just another graph that looks at the power that is lost as a percentage. So as an example here with the previous set of data here on this left graph, if we look at the power loss, what we see is that for that 2.7 millimeter via structure, what we have is almost 40% of the power is lost. Here is a good example here. When you're at about 80 gigahertz, you see a lot of the power is lost in that particular structure. And you can pick off different values from this graph. It's pretty clear what these peaks correspond to. For the VL equals 0.4 millimeter structure, the bandwidth is all the way up much higher beyond 100 gigahertz, and that's exactly what we saw in this graph. So we have very low power loss due to these resonances because they don't occur up until much higher frequencies. So just as an example on the left side, we have a coplanar waveguide here. This particular coplanar waveguide uses 2.042 millimeter spacing on our very thick layer of Rogers. Now, this very wide transmission line here is going to have lower skin effect losses at our operating frequency. We also have a low loss dielectric. So the reason this particular structure was designed in this way is that, number one, by using 30 mil dielectric, so a thicker dielectric between the top layer and the ground plane, you have to now use a wider trace to get to a 50 ohm impedance. You absolutely have to use a wider trace. You have no choice. That's what's going to give you a 50 ohm impedance. But by using the wider trace, you're going to have lower skin effect and you will have lower conductor losses. Now, if we look at the via spacing between along the edges of the structure, so at 2.042, you can calculate that you will get reliable 50 ohm impedance up to about 42 gigahertz. Okay, so here in this example, right, 2.042 millimeters is about double VL, right? So it's essentially this width. Okay. And so what this is telling you is that right at lambda over 2, or right at the frequency corresponding to a half wavelength equal to this distance, that frequency is where you will see this first peak in this power loss spectrum. And that frequency just happens to be 42 gigahertz. So this particular structure could reliably transmit power with low loss up to 42 gigahertz. If we wanted to extend this operating frequency range much higher, what we would need to do is use a thinner trace so that we could bring these vias closer together, but that would also require using a thinner dielectric. And as a result, we would then have higher conductor losses. So this should illustrate some of the different trade-offs that we have in RF PCB design and in RF interconnect design. So next, I want to talk about substrate integrated waveguides. So this very unique structure that we see on this test board with this SMA connector is a substrate integrated waveguide. Now, on the left side of the structure, we have a controlled impedance microstrip. So here, this microstrip is designed to 50 ohms. And this taper region provides impedance matching between this 50 ohm transmission line and whatever the impedance is of this structure. Now, this is very important because the impedance of this structure is not 50 ohms. It's actually something more like 200 ohms. I believe. I'd have to calculate it. But this particular structure is very wide. Now, there's actually references that you can find that will help you calculate this taper length so that you can size this taper appropriately, and you don't have to actually worry about calculating the wave impedance inside of this structure. You don't really need it for the application that we're going to look at here in just a moment. But this particular structure allows you to transmit at just one mode, so meaning at just one specific electric field distribution. Now, that can be very useful because let's say we want to excite a specific electric field distribution inside of this structure. Well, if we then put a slot in the copper in this structure, we've now just created a slot antenna. And that slot antenna can broadcast very strongly, even in a lossy dielectric like just a standard FR4 dielectric. And so I've actually built Wi-Fi transmitters based on this structure. And this particular structure broadcasts very strongly at Wi-Fi frequencies. If we were going to use it at much higher frequencies, what that would allow us to do is make the structure smaller. And then we would also want to use a low loss dielectric in that structure. So the advantage here is the ability to transmit at just one of these modes or at multiple modes. And there's quite a few different parameters to consider here, right? We have the diameter of these vias. We have the spacing between via centers. So this is A sub SIW, meaning this is the width of the substrate integrated waveguide. Then we have the height of the structure, or the thickness, I guess you could say, of the dielectric. And all of these go together to give you a particular size and set of wave numbers that you can transmit through this structure. So this wave number here, K sub NM. N and M are integers here, okay? And this K is just 2 pi divided by lambda. And so the idea here is we'd like to determine the wavelengths for a given frequency that will then propagate down this particular structure. And the reason for that, or the reason I would want to know the wavelength, is because if I have a slot here in this particular structure, I would like to know the span of the wavelength that is then interacting with that slot. That tells me how big I need to make that slot in order to ensure that I'm transmitting maximum power out of that slot. So these K and M values, essentially what I do is I plug in a frequency here for my SIW size and then for my height above the reference plane. And then n and m being integers, this essentially just tells you or indexes these different modes that you excite at different frequencies. Okay, and this is going to tell you the different frequency ranges where this structure can guide a wave between a transmitter and a receiver. So to calculate all of these different terms, first we need to design a taper. The taper is very easy to design within even at millimeter wavelengths. There's a reference here that gives an empirical formula that can be used. So the taper length is known. You can also get it from some simulations doing something like in Symbior, for example. Then we also have the feed line. The feed line width here at the taper end also depends on the width of your microstrip line. So remember, the microstrip line is sized to 50 ohms. So it hits a 50 ohm impedance, and whatever that width is, you plug it in here. And then the width of the substrate integrated waveguide is matched, or is used to match this taper width. Okay. So we have some values that we get to choose. It's W and then A sub SIW and then the frequency, and we plug those in here, and then we can use that to get these different terms here in terms of the width, the equivalent width, and then we can use that to calculate the frequencies. So let's just suppose for a moment we want to have a cutoff at 5.725 gigahertz for this structure that we're calculating. So this would support 5.8 gigahertz Wi-Fi. I use this value here because this is the bottom end of the channel in the 5.8 gigahertz Wi-Fi standard. So you can find that in the 802.11, I think it's AN or AX standard. I forget the alphanumeric character on that, but you can find it on Wikipedia. So anyways, this is the lower frequency cutoff for the lower end of that Wi-Fi band. And so doing that, we can calculate what the equivalent width of our substrate integrated waveguide is, and then we can use that to get the actual width that we need to set in this particular structure. So once we know that and we know our dielectric constant, we pick some via spacing, our diameter and pitch. We use all of that together to get our microstrip width and then our taper width and our L sub t value. Then we get our real substrate integrated waveguide spacing. And so using this, we can then get the cutoff frequencies. So when I take this and I use that to calculate the cutoff frequencies, these are my results. So what this is telling you is that I can transmit a mode that has an electric field distribution that looks something like this between 4.5 and 9 gigahertz. Any frequency between 4.5 and 9 gigahertz. Okay, so if we're operating at 5.8 gigahertz Wi-Fi, we could transmit that frequency and any other frequency within this range inside of this structure that we've designed here. So with this via diameter, this via pitch, and then this spacing between the vias, and then of course these taper parameters. So that's what this table is telling you. Now, this table is also telling you that you could actually transmit also between 9 and 13. However, you're going to have a different mode distribution. So instead of it just being this one mode, like we have here in this 50 gigahertz example, it could look something like this, where we have these two lobes distributed across the cross-section of the substrate integrated waveguide. So that electric field or magnetic field distribution that you excite in that structure is really a superposition of the 1 to 2 distribution and the 2 to 3 distribution. So you can get this type. You can design the structure to accommodate these different modes that then transmit down to a receiver. So I had mentioned earlier that you could use this as a slot antenna. And so there's a really good paper here that I've cited from IEEE down at the bottom of the screen. And that particular slot antenna is the type of thing that we've used with Wi-Fi. In this example, they used it, I believe, at 33 gigahertz or at 17 gigahertz. It was pretty high frequency. But what they did is they found that if you place the slot just off center from the axis of the waveguide, when you're operating between the 1 and the 2 mode, what you can do is you can get very strong impedance matching and transmission of a harmonic wave into a waveguide from this slot. And so this uses a double ridge waveguide where this ridge structure then matches this waveguide impedance. So that's this vertical rectangular structure to the impedance of this slot and the substrate integrated waveguide. So this is strong enough to damp or to swamp out many commercial Wi-Fi receivers that you will find on receiving components. The other way you can use this is as an edge emitter. And you could really do the same thing with just a standard coplanar waveguide, as long as you had this kind of structure at the back end of it. So this particular edge emitter structure would transmit a harmonic wave with this type of power profile looking at the edge of this structure. Okay, so this structure would transmit out the edge. And the level of transmission, or the amount of power that this emits, is going to depend on the impedance matching to 337 ohms. So this is a situation where you actually do need to know the characteristic impedance of this particular structure. So this particular structure will have some characteristic impedance, and it needs to then be matched to 337 ohms. And so the typical way you would do that is, because this is essentially terminated as a short circuit, you then need to adjust the length of this structure so that the input impedance at this wide end of the taper is equal to 337 ohms, because you have a 337 ohm load out here that needs to then match to a 337 ohm input impedance here at the wide end of this taper. So next I want to move on to phased arrays. Phased arrays are another type of emitter, and this is where it starts to get really fun with RF design, because these arrays are used for beamforming and for MIMO applications, or multiple input, multiple output applications. So some examples, Wi-Fi is actually one example. The newest standard of Wi-Fi allows for multiplexing, so MIMO multiplexing. That multiplexing can be done spatially, meaning that I just dedicate, let's say, these 4 antennas to one Wi-Fi user, and then these other 4 antennas are dedicated to another Wi-Fi user. This can also be done temporally, meaning that within one time window, I only communicate with one user, and then within the next time window, I only communicate with a different user. Okay, and so that is multiplexing applied to MIMO. Now, the way that these phased arrays work is they broadcast along a specific direction. And so the distance between these emitting elements needs to be set such that the distance that you want to or the angle that you want to transmit at is now a function of this wavelength divided by some number. Okay, so let's just suppose that I want to get my transmit at very strongly along, let's say, a 45-degree angle. Okay, well, I can do that as long as this distance between these two elements is less than this limit. Well, so I would plug in 45 degrees here into theta sub max, calculate the cosine, add 1, divide these two, and then given my wavelength in air, that tells me what my distance has to be for my transmitter. Same thing applies to a receiver. So phased arrays also work as directionally sensing receiving elements. So if a wave comes in from a specific direction, it will excite a signal in these receiving antennas with a different phase in each antenna. So there will be a phase difference. And that phase difference can be detected in this beamforming IC. So beamforming works in reverse, and it works on the receiver. And so using that phase difference between these two waves, you can then figure out the angle at which those waves arrived. Okay, and that's a pretty simple calculation. So it works in both ways. So you can transmit at a specific angle, or if you want, you can detect the angle that your antenna array received at. So I mentioned Wi-Fi as one application of this. But another common application is in radar. Now, in radar, if you look at like a radar dish, let's say even like an old radar dish from like a Cold War era radar, it might not be obvious, but that radar is actually using multiple antennas, and those antennas together form a phased array. So this is also used in radar. Now, in radar, this phased array has a transmitting section and a receiving section. So this transmit section is over here, and then the receive section is over here. So in this particular example, where we have these 3 transmitting antennas and then these 4 receiving antennas, this is an example from an NXP design. This NXP reference design operates at, I believe this is a 77 gigahertz radar. It may be a 24 gigahertz radar, but even then, they still can do MIMO with 24 gigahertz. But I believe this is a 77 gigahertz radar. And this is all a single board design. So we have all of the digital stuff on the back side, and then we have our transceiver on this top side, and that transceiver is then connected directly to our antennas. These chipsets that are being used, and especially the newer chipsets, they really try to integrate all of this processing and signal conditioning into the transceiver. So there will be a DSP block, which is then used to get apply signal processing to the received radar signals. It's also used to apply chirp to the transmitted signals. You have communication interfaces with a main controller, so you can configure the device. You don't necessarily need external power amplifiers in these highly integrated modules. So all of these newer components have all of this stuff built in. So another example here where you can actually see how these lines are routed is in a 77 gigahertz radar. There's a couple of reference designs that I like to show. So here in this left one, you can see this white background here, this white substrate material. That is Rogers. So this is a Rogers material. This particular one is not immersion silver, but you could get lower losses if you go with immersion silver. And a better way to do this, in my opinion, to ensure better isolation between this radar section and other stuff on the board, is actually to use a coplanar waveguide. And in this case, they used blind vias in this example design on the right. So you might wonder, why blind vias? Why would you use blind vias instead of through-hole vias to line up all of these to line along the coplanar waveguides here? Well, the reason you could use through-hole vias. It's perfectly fine to use through-hole vias along a coplanar waveguide. But the reason that you would use blind vias is because in this particular design, you could have components on the back layer. And if you have a bunch of through-hole vias here, those through-hole vias can interfere with component placement. So now you really couldn't place any components in this region on the back layer where my mouse is, because you'd have all these through holes poking through to the back layer. And so by doing all of this with blind vias, you eliminate all of that. And you only have these blind vias spanning from L1, which is where you see the antennas, over to the next layer, which is our ground plane. And so that allows you to put components on the opposite layer. Now, these patch antennas are intentionally designed to provide very high gain within a relatively narrow bandwidth. And so that gain can be visualized in one of these charts or using this kind of radiation pattern. So this particular example was done in ANSYS. So you can see here, it says ANSYS right here, but this particular example is showing the return loss, so the S11, S parameter, looking into this antenna from this port here, so the lower left portion of the screen where the antenna begins, that's our input. And then you see we have very strong matching to this particular, at this desired frequency range. So we have very good matching, which means there's very little reflection off of the input port of this antenna. So this antenna is very approximately, has an impedance of 50 ohms. So all of these patches are additional emitters, and these patches are all radiating very strongly. And that's what gives you this high gain. So when we talk about antenna gain, what we're talking about is the directionality of this antenna. And so you can see it here with this heat map. This heat map shows that we have a maximum gain of 13.1 decibels. Or in other words, it's about 1.3 times stronger in this one specific direction compared to a uniformly emitting antenna. So this is a good result for a patch antenna, and if you want, you can go ahead and use this design if you like in your own designs. But this particular antenna example is very typical of what's used in like a radar application. So I had mentioned before that MIMO is one thing that you can do with antenna arrays. Now, typically what you would do in older radar systems is you would control the direction of transmission. So you would control the direction of the emitted beam by modifying the phase difference between the signals that are being sent to each of these antennas. So by modifying by setting a phase difference between the signals that are sent to each antenna, you then cause them to superimpose very strongly and broadcast very strongly along a specific direction. Now, the challenge here is that the direction that you emit at may not have very high resolution. And so this is one of the reasons that radar systems are very good for detecting where objects are and what their velocity is. But if you look at like newer cars, the radar system is only telling you where an object is at kind of generally. So like backup cameras that include a radar sensor or an ultrasonic sensor, they're just telling you that there's an object within the field of view, and that's it. So radar systems that are going to be used for autonomous vehicles need to have much higher resolution. And MIMO is one technique that you can use to get much higher resolution. So the way that this is done is that in a MIMO antenna array, you have the freedom to pair up TX and antennas and RX antennas that are operating at different frequencies to create a virtual array. And what that means is that even though in this example I only have 7 antennas in my array, it can act like a 12 antenna array, as I've shown here on the bottom. And so when they all work together and send and receive simultaneously, even though this may be at different frequencies depending on how multiplexing is applied, these antennas are going to act like a much larger antenna array. The reason we would want to do that is because this angular resolution or the angular span on our emitted beam can actually be made much smaller by adding in more and more antennas. So I like to show this example reference design because this example reference design from Texas Instruments uses a set of 4 transceivers, each with 4 RX arrays and 4 TX arrays. So here we have a 12 times 16 array. So you can already see, just as an example, what the size of that virtual array is going to be. And along this horizontal scan direction, this particular array actually gives you less than 1 decibel resolution. So if you wanted to track multiple objects with a particular radar system, what that means is you now need to have a lot of antennas all broadcasting at once. And this is why we use a MIMO approach with these particular systems. Now, the MIMO approach allows us to say, use these 8 antennas, so this is 6x8 array, I should say. So maybe use these 2 transceivers to track one set of objects, and then use these other 2 transceivers to track another set of objects. Or they can all work together and get very high resolution images of a surrounding scene just using radar. So you wouldn't necessarily need to use images. The other thing that you can do is you can use that very high resolution for depth sensing and velocity sensing along with a visual image. So like a photograph, something captured with a camera. And that would then take the place of a LiDAR system. So using a camera system along with MIMO radar allows you to build a velocity and distance resolution map that then tracks a large number of objects in a scene. So you'd have to apply some AI to get, in order to get, to do some object extraction from that vision image, and then pair that up with data from your radar image. But doing that, you can then track the velocity and distance of multiple objects in a scene. So I mentioned that in MIMO, in order to get these high resolution images, there is a motivation to get as many antennas as you possibly can onto a PCB. So this is an example here from a company called Arbe Robotics. This particular example shows a large number of antennas. And all of these antennas are laid out kind of in this RX and TX stack. So it's not clear just from looking at it which of these are RX and TX. But what this is doing is they're laid out in this way to enable sensing not just horizontally here with this array, but also vertically. So you get very high resolution both horizontally and vertically. Then you have to have some vias in order to reach all of these different antennas. So I had mentioned earlier that, it's often stated that you should never use vias on RF signals. And generally that's true. It's a bad idea to use vias because vias are often not designed properly for RF signals. However, in some cases you really don't have a choice and you absolutely must use vias. This is one example where you have to use vias. Another example is actually in this design because all of these chips have to be synchronized so that you can define a definite phase difference between each of the signals sent to the antennas. And so that requires a low frequency oscillator on an internal layer. So on L3, there's a low frequency oscillator that then has to pass through vias in order to reach each of these chips. So in some cases, you absolutely must use vias. Now, the preferred way to use vias with RF signals is actually to use a blind via or to use stacked microvias. And so you can see an example here from this paper that I've cited. These stacked vias then feed in from an internal layer and then reach a set of antennas up on the top layer. Okay, so those vias need to be very carefully designed so that they have approximately 50 ohm impedance. Now, the caveat here is that with these stacked microvias, one of the reasons that you might want to use stacked microvias on very thin dielectrics is because when this via is very short, it doesn't look like a transmission line. And so the signal that's incoming essentially only sees the input impedance from the destination transmission line, and the vias look partially invisible. Okay, so this is a consequence of short transmission lines. Essentially, these vias act like short transmission lines. However, if you're using larger vias would require a through-hole approach. So let's say you were routing something from the bottom layer all the way to the top layer. Well, now you need through-hole vias. And for those through-hole vias, you need to design them such that they have 50 ohms impedance. And that's because at these frequencies, say 77 gigahertz, those longer vias are going to look like transmission lines. Now, there is a simple via model that you can use to calculate the impedance of a via. Unfortunately, it is only correct in situations where you don't actually need the via impedance. So there have been multiple people posting on my LinkedIn recently that they've come up with a via impedance calculator. I'm going to tell you right now, those via impedance calculators are either wrong, they don't give the correct results, or they're only valid in a situation where you don't need the via impedance. And it's very easy to see why this is the case. Those via impedances that they are returning are constant values, but the reality is that when you have a long via, and when I say long, it's long compared to the wavelength of this signal that you're transmitting, you're exciting a resonant cavity here. And so when you're exciting this resonant cavity, you're going to have peaks in the S11 and S21 spectrum. And that means that you have frequency regions where the impedance is not 50 ohms. Even though you may have designed that via to 50 ohms, the impedance is actually not 50 ohms. So what that means is that these simple models where you have a trace coming in and then you're using this pi model to get the via impedance are ignoring the fact that you have a wave propagating on this interconnect. So this is not a transmission line model, and it is incorrect. Now, it's reasonably correct at low frequencies, and it gives you a low pass cutoff for this particular structure based on the pad diameter and the anti-pad diameter for these vias. But those are situations where you actually don't need to worry about the via impedance. So this is something that folks who are making these via impedance calculators really, I don't think, understand about signal propagation in vias. A real via transition that is going to operate at very high frequencies looks something like this. So first of all, you don't just have the via, you have stitching vias around it, and all of these stitching vias are connected to ground on the next layer. So here in this structure, I have a transmission line with 50 ohm impedance on the bottom layer coming in. I have my receiving transmission line up on the top, and then I have some stitching vias around it. And these stitching vias are used to set the allowed modes that are excited in this cavity. And then this signal via is here in the center, and then I have a ground plane cutoff. So this structure essentially looks like a big cylindrical resonator. And I say big with an asterisk next to it because it's actually not that big. If you look at the size here is actually 36 mils. But this particular via structure could give you high transmission up at from the 71 to 81 gigahertz range. So this is something that you could use for radar. However, you are like right at the edge of manufacturing constraints with standard manufacturing processes. So in standard mechanically drilled manufacturing processes, these stitching vias are already at 8 mil diameter. This is going to be the limit that a lot of fabricators will accept in their process. Now, they could do 6 mil drilling for these stitching vias, and that would allow you to get a little bit more control over the size of this structure. But here we're really running up against the limits of what you can reliably manufacture using standard etching and drilling processes. So getting to higher frequency vias requires an HDI approach, or you're not even going to be able to do through holes on these designs. Okay, that is all that I have for now. We're running up against our time limit. So I would like to thank everybody for attending this webinar. I hope you all found it very informative, and I have some time now to take some questions. So I'll go ahead and open it up for questions. Hold on just a moment. Let me unmute. Oh, wow. Well, it's not allowing me to unmute here. So if anyone has questions, feel free to put them in the chat. Here's what I'm going to do. I'm going to give all of you guys my personal email. So please don't spam me, but if you all have questions, I encourage you to type them out here and send them over to this particular email address. So please go ahead and send me your questions. Let's see here. And yeah, go ahead and send me these questions, and feel free to ask me anything about this presentation. I'll do my best to get to them as fast as I can. I'm usually pretty busy, but yeah, feel free to send me your questions, and I'll do my best to answer them. So thank you again, everybody, and